Today we're going to talk about something pretty cool that has the potential to revolutionize technology, superconductors. But in order to understand how they work, first we need to talk about current. Current is the rate of flow of charge from one point to another, which is carried by electrons. Substances that are good at moving this charge have a very specific chemical property. If a substance has a lot of free electrons in it, it's easier for the charge to move through it, which is what makes it a good conductor. Metals are often good conductors, for example, because many of them have what we call seas of electrons when in elemental form, and this allows the charge to flow easily from one atom to the next. Substances that have a more constricted flow of charge are called semiconductors, and those that impede the movement of charge almost completely are called insulators. Every substance, even conductors, also have some resistivity. This is how much the element or compound resists the flow of electrons through it. Substances that are more likely to hold onto their electrons tightly have a higher resistivity. Each substance has a specific resistivity represented by the symbol ρ, but its total resistance, represented by the letter R, can change depending on the size and shape of the object. For example, if you increase the length of a wire, it's harder for an electron to get from one end to the other, which means that the total resistance increases. This is because the further the electron has to move through a substance, the more energy it takes. This relationship is represented in the equation R equals ρ times L over A, which takes into account both the length of an object and the area when talking about the resistance of a cylinder. As you can see, resistance and length are directly proportional, but area and resistance are inversely proportional. As you increase the cross-sectional area of a substance, it can hold more electrons and thus allow for more current to flow through. Resistance is also temperature dependent. As a conductor gets hotter, the atoms in it and the electrons moving through it have more energy, which causes them to bounce around a lot more, which also causes more collisions. With so much movement of electrons, it becomes much harder for a current to travel through the substance. This can be represented by this equation, R equals R naught times 1 minus a constant alpha times the change in temperature. In this equation, the resistance and temperature are directly proportional. As you increase the temperature, the resistance also increases. And here's where superconductors come in. For some substances, when the temperature is very low, the individual molecules are moving so slowly that it's easy for a current to flow through them because the electrons can flow completely freely. This drops the resistance all the way to 0. The temperature below which a substance becomes a superconductor is called the critical temperature, and for most conductors, it's close to around 0 Kelvin. So what can you do with superconductors? Since their initial discovery, superconductors have made important impacts on the world of medicine and technology. One of the most common uses for superconductors is in MRIs. Since all current causes a magnetic field and superconductors allow current to flow freely, they can induce the very powerful magnetic field needed for MRI machines. This magnetic property of superconductors has also been used for trains that use magnetic fields to float on the tracks in order to increase the speed and reduce friction. The large amounts of energy that can be created with superconductors can also be used to power things like supercolliders. The ability to transfer current with no resistance also has a lot of potential in power transmission. Electric generators made with superconducting coils could produce more energy more quickly because there would be no resistance in the way. The same principle applies to the wires that bring electricity into your home. Using superconductors would increase the efficiency of this process dramatically, lowering overall costs and reducing unnecessary energy use in electricity production. So all of this begs the question, if superconductors would work so much better than the current technology, why aren't they being used more now? Well, there are a couple of challenges to large-scale use of superconductors. Since the critical temperatures are so low for most conductors, a lot of energy is required to maintain those temperatures for a sustained period of time, especially over a large surface area. For example, it'd be very difficult, not to mention costly, to keep a power line that stretches for miles under 10 degrees Kelvin. This challenge has led scientists to try to find superconductors with higher critical temperatures. Several high-temperature superconductors have been discovered, which are mostly made of different ceramic compounds. While these are cheaper to keep cool, The ceramics themselves can be fragile and expensive to manufacture, which also makes them difficult to use for power transmission. They can, however, be used on a smaller scale, such as in cell phones, to filter out unwanted radio frequencies, but they currently aren't viable for widespread use. Though there are many challenges to using superconductors, as synthesis technology improves and as we gain a better understanding of high-temperature superconductors, they could really change the way that we use power. Who knew that the temperature dependence of resistivity could be so useful?